Hello, everybody. It's great to see so many of you. Thank you very much for joining us. And my name is Melissa Cogbin. I am the editor of Broadband Journal. I know some of you already, and thank you very much for joining us. As you know, we introduced webinars during lockdown, and they've proved really popular. And we're back here with Technetix for the third time. We must be doing something right for them to take the plunge with us again. So thank you very much again to Technetix. Today's webinar is entitled Reduce Your Network Power Costs by 25 to 30%, hosted by Jan Ariesen, Chief Technology Officer at Technetix. He recently celebrated 40 years in the industry, which is a fantastic achievement, but it's also a testament to the passion that so many of you feel about this industry as it's evolved over the years. So just a couple of messages on the housekeeping side of it. Jan will be doing all the talking today, and we're all listening, obviously, but we'd really encourage questions as we go along. So if in the Q&A function at the bottom of the screen here, if you want to add your questions there, and we'll read those out at the end. The whole event should take about 45 minutes plus the Q&A at the end. And if you have any particular questions you want to raise during the session, do raise your hand and I can address that. I think that's all from me. And I was going to suggest, I was going to go into a lengthy bio about Jan's significant achievements, but I don't think that's necessary. You all know all Jan, so he's better placed than I am to explain what we're discussing today. So I'm going to hand over to Jan Ariesen, and thank you very much. Enjoy.
Thanks, Melissa. Did you switch the video?
Yep. Sorry, what do you need me to do?
No, I thought you switched the video. I don't know if that's done. Okay, great. Thank you thank you all for joining. As Melissa said, today we're going to talk about power reduction in the cable network. We know we are building the cable networks for many years. As Melissa, you said, I'm here now for 40 years. See a lot of changes over time. Maybe we just had a few TV channels and some radio, and then at a certain time in the 90s, end of the 80s, we went into bi-directional with special filters and so on. And from that moment on, we keep on doing more and more over the coax. The way how we power the network is still roughly the same as what we did a long time ago. We still have the power supply to feed all the active components via the coax cable. And that's something that we would like to discuss today, if we do this the right way. And are there alternative ways to do this better or with reduced power? So, okay, let's go to the presentation. And the presentation is called Access Smart Powering. So it's about how to power the access network. What I want to discuss today in the presentation is to set some goals. I want to say, okay, what can we do to save energy? Another part is what can we do to lower power consumption, be more green, get closer to your net zero goals. Everybody has their goals, it's 2035 or another number. They said, oh, we want to be net zero around that time. Still, a lot of power is used in the cable network, and by reducing the power is a big step to meet that goal. And of course, at the end, this will lower the OpEx. Everybody knows that power prices only goes up, and reducing power consumption in the network at the end will reduce your power bill. And what we want to do is we do this only by changing one product. We want to change one product per service group. So the power supply of the node, that's the part that we are going to address of all your service group. And with changing that part, we want to reduce the power. And the agenda of the presentation is that we want to first give some background information about powering. We want to do the current approach. So how do we do it at the moment? What are the alternatives way of doing it? What are the results of that testing? We also did some testing in the field about what is the impact of the battery backup. This also helps there. And then also some pros and cons about this concept. So let's first see the power. So if you see this is done by the Energy 2020 group in the US. And they did some research, where is the power of the MSO used? And as you can see, roughly half the power bill is used in the outside plant. Of course, you have data centers, you have buildings, you have a lot of other parts in it. But the main part of the power consumption, the biggest part of your power bill, is still the outside plant. And that's switched on 24/7. So this is something that is a big contributor to your power bill. And that's something that we want to address today. How does it work? When you have a network, so a simplified network, we have a few amplifiers like this. Then normally we have a transformer. Inside the transformer, one side we have the mains, and the other side we have a lower voltage, and that voltage goes on the coax, and that will go over the coax through all the active components to feed those components. So the coax is there not only to distribute RF channels up and downstream, but also to do the power part. That's all going via that same cable. And how that is done inside the amplifier is quite unique, I want to address. And also the way how we put the power onto it. The way how it's done mostly, it's not always, but mostly is done by a ferroresonant transformer, a constant voltage transformer. But the way how that is done is you have your normal transformer, and then you have extra winding there to saturate the transformer, that the voltage will not go above a certain. Therefore, you can see instead of having a sine wave, we are topping off because at that moment the iron pack gets saturated and will not go any higher than that. There are two ways of doing it. We have single conversion and we have double conversion. They both have their pros and cons. The single conversion efficiency is about 92 to 94%. Yeah? And the power factor is somewhere between 85 and 0.9. So that's roughly 0.85 and 0.9. That is single conversion. Mostly double conversion is used, and that's also because it has a better entrance for the better backup battery powering. So double conversion is mostly used, and that means that you have twice this step, and therefore you can see that the efficiency is lower. That is between 69 and 83%, and that depends a lot on the loading. As I said, you have that big iron pack that you have to magnetize. That will cost you 40, 50 watts or whatsoever to put in there. And if your network is only 200 watts, then you can imagine your efficiency is very bad because you lose already 50 watts here to deliver 200 watts in the network. If your network is 500 watt, the contribution of that 50 watt, of course, is lower compared to the whole network. So efficiency depends on the load. And it's somewhere between 69 and 83%. But your power factor is better. It's about 0.92 or 0.94. That's what you have with double conversion, and mostly double conversion ferroresonant transformers are used in the network. What do we do with this voltage? This voltage goes onto the network and therefore has a power factor. Because you have your voltage going on there, and that voltage will go into a resistance load, and they call that the real power. So the real power that you put on the network is the voltage times the real current. And you can see here, that is the real power, is the voltage that you have times the real current. That is the real power that we have on the coax network, or the network. Unfortunately, it's not just a resistance. It can be inductive or capacitive, and therefore you also have some reactive power in those parts. And the combination of those two is the apparent power. And the apparent power is the power that we really transport over the coax. As you can see here, I try to put this in a line so that the real power is the voltage times the resistance loading. The reactive power, the Q, is the voltage times the capacitor or inductive power. And then you have the apparent power, S, this one here, is the vector magnitude of those two. And that is in fact then the voltage times the current that you have. So you see that we always have the same voltage, but the current differs. The power factor is in fact the relation between the real power and the apparent power. So why is this important? This is important because the apparent power causes cable losses. I try to explain this here. And a power factor of 1 means that there is no reactive power and the apparent power is exactly the same as your real power. But if your power factor is lower than 1, 0.8 or whatsoever, that means that your apparent power also contributes to your losses. It's not something that you have in the amplifier, because the amplifier is using that real power. That's not the problem. The problem is that the power that we transmit over the coax network is higher. And that is related to that apparent power. and because the power that we transmit over the coax cable is higher, the current will be higher, and the current causes losses. Current is higher, the voltage drop will be more, and therefore the voltage is lower, and therefore the current goes up even more. So you can see that the power factor has a relation to the losses in the coax. Not so much with the amplifiers itself, it has a relation that when the power factor is worse, we're going to lose more power on the coax. So I also try to explain that here, that the power draw from the network goes up. That is when the apparent power goes up, then the current goes up, and it means a higher power loss. And that's important. It's important for if you look to the network. That's why sometimes people say, oh, we go for power factor corrected amplifiers. Because if the power factor corrected amplifiers, that will help us to bring the apparent power closer to the real power, and therefore the losses that we have on the coax will be lower. And that's true. The closer you get this to the real power, the lower the losses will be on your network. This is about the power factor. So this is some theory about ferroresonant transformers and about power factor. And this is all important because at the end we want to see, okay, what can we do to save power? If I look to the amplifiers or every active device roughly works the same. Especially nowadays, if you look to the last 20 years, everybody has called the switch mode power supply. Switch mode power supply is very power efficient, and that will help you with the power draw that you get out of the network. In the past, we had linear transformers, and then you had a much worse efficiency than we have nowadays with switch mode power supplies. So I don't think that linear still exists. So how does that work with the switch mode power supply? In switch mode power supply, we have a voltage. So let's say that we have a voltage going up, and when the voltage goes up, what you see is that they will conduct, and when you have the negative cycle, the other two will conduct diodes. So the output will be that we have twice a positive half sinus. So although the input sine wave, so although the input voltage is like this, and then the output voltage out of this circuit will be that you have two positive sine waves. That's the first step. Then we're going to put a capacitor here and the power supply. So what happens now? Same idea. Let's say that the voltage goes up. So what you see here is that there was still a voltage here. So that voltage is that black line here. On a certain moment, the voltage on the input is higher than the voltage we have here. On that moment, those two diodes will conduct, and then you see that the voltage goes up again. Because then the voltage here is loaded by the voltage here. So there will be energy going in this direction, and that will load this capacitor, and therefore you see it goes up again. If I get my second half here, then you see that nothing is conducting because the voltage on this side is lower than the voltage I have on this side. Therefore, all those diodes stop conducting, and you see that the voltage roughly stays the same. It goes down a little bit because we are drawing power out of these capacitors to feed the amplifier. Therefore, you see that the voltage will go down a little. Although the input voltage is like this, the output voltage on this capacitor, you see, is slowly dropping. The higher of the current we draw out of it, the more rapidly this will be discharging. And then we get the second half, goes the same. And those two will start to conduct on the moment that this input voltage is higher than the voltage we have here. And then you see that the other two starts conducting, and you can see it goes up again. So this is the way the voltage that we have here inside the active device. The voltage is rectified by this rectifier bridge and is stabilized with this capacitor. And it's only discharging is due to the current that the amplifier will take out of it. Why is this important? This is important if we start looking to the current. If I now do the same, and now I'm going to add the current to it. So in the beginning, the current is zero. It's zero because on this part here, the first part, nothing is conducting. So I have no current floating in here. till I hit the moment that those two start to conduct, because the input voltage is higher than this here. On that moment, I have to charge my battery here. And therefore, you see that the current suddenly goes up, because that is the loading current of this capacitor. Then, when this drops again, nothing is conducting, so all my current is zero. There's no current floating. Then I get my second half, and then the same. On a certain moment, the voltage is higher. Then they start to conduct to feed this capacitor again. And again, I have this huge current. This continues like this. So you see that although the input voltage is a sine wave, the input current, the current that we have in the network, is a peak. There are two peaks, a positive and a negative peak instead of a sine wave. And that is important if I look to the networks, because this is not just one device. There will be multiple devices like this in the network. But this is what happens inside the switch mode power supply, that you're going to get those two peaks. So if I now look to a network like this, and we just have our voltage like this, that we just saw, that we have the sine wave voltage on the network, you will see if I look to this amplifier here, the current are two peaks, a positive and a negative peak. That's what I have here. But it's not only this amplifier, it's also all the other amplifiers are doing this. And if I look now to this amplifier will have the same peak, but this cable here is this amplifier plus this amplifier. So the peak is even higher, because it is this peak plus this peak. And therefore the current that I have in this line is even higher. Same as here, same as here. So if I now look to those two cables here, they have to do the peak of this one, and the peak of all these other amplifiers. And therefore you see that the peaks even get higher here. Of course here it's the highest. So you see that although the voltage is a sine wave, the current is just a large positive and negative peak. The results of this is, why is this important? Is because if you look to a coax cable is like a resistor. It's a low resistor, probably about 4 ohms loop resistor per kilometer or something like that. So it is not that it is a unit, but it's a resistor. And according to Ohm's law, we all learned that part, is the power is I square R. So the I square times the R. The R is constant, but the I are 2 times a peak. So the power loss that we have in this coax is a lot if the peak is higher. The higher the current, the higher the loss. And that's important if you look to a network like this. Because at the end, we don't want to lose that power. We want to give the power to all these devices, but we don't want to burn power in the coax. And we want to make that as low as possible. But unfortunately, we cannot change the coax, so the coax will have a resistance. So the only thing we can address is the current. And if you now look to the power that this transformer has to deliver, and then in fact the power that we have to put in here to deliver the power, to deliver it all to the network, is the power that I have here is the power of all those amplifiers, plus the power of all the cables that I lose. I lose a lot of power in all the cables. And so I add those two up, and then I divide it by the efficiency of this transformer. That will be, at the end, is the power that I have to draw from the network. If I do the same on an alternative way, and one of the things that we looked into is that, okay, what if we feed the same network, but then we want to change the current? That's what our drive was, our first drive. So we said, what if it will go to DC powering? Same amplifier, same stuff, but now we have a constant voltage. So here we have a constant voltage, and also we have a constant current, the 2 purple lines. So the current now is a constant current. It's not anymore a peak up and down. It's just a constant voltage and a constant current. And we just have those two conducting constantly. Because you are just, so in fact, all the current that we put in here is only to feed the amplifier. because we don't have to charge this capacitor anymore. All the energy goes straight into the amplifier. So what you see now is that the current is much lower instead of two positive peaks. The energy is maybe the same, but because the shape is now a constant shape, therefore the current have a much lower value. And if I do that now the same with my same network, where I have a DC, and now I have a AC-DC converter here, now I have the same formulas. My power loss is still my I square R, but my I is much lower. Because now it's a constant current. I is much lower, therefore my power loss is much lower. And in combination to that, I still have the same formulas, that the power P here is still all my amplifiers, plus all the cable losses, divided by the efficiency, in this case, of the AC-DC converter. And those two elements will make a big change on the coax network. So we look to a network like this, N+4 network, where you have 3 trunk amplifiers, and then we have a number of line extenders around it. So it's about 300 meters of coax between the amplifiers, 55 watts for the bigger ones, 30 watts for the smaller amplifiers. Just a network to compare apples for apples. And what we looked into is that, okay, what will happen if I have a quasi-square 89 volt top voltage, or I have an 89 volt DC voltage? What is the impact on the network? Calculated it, tested it. So to give you an idea, if I look the same network, it's a different way of feeding the network, then the network, the amplifiers are both types, 550 watts. The power factor this time was about 0.8, and here I have with DC, I have a power factor of 1, because there is no mismatch between capacitive and inductive loading on a DC. So that's always a 1. So therefore, you see that a big difference is in the cable loss. The cable loss in this case with quasi-square is 214 watts in this situation, and on DC is 115 watts. And that's just because the amplitude is lower and my power factor is 1. Because again, because of my power factor is not being 1, means that it looks like all these amplifiers have a higher apparent power. Therefore, the current to go through the network to feed the amplifier is higher, and therefore again, the loss in the coax is higher. So that all adds up, and then you can see that the total power I need here in quasi-square is 769 watts, and with DC is 670 watts. And then I have the second step, as we saw, is that with ferroresonant transformers, we have an efficiency somewhere between 69 and 83%, while an efficiency of an AC-DC converter is around 94%. And that, of course, gives you then the other saving, and therefore you see that this time, with the quasi-square, we need to draw out of the network 961 watts. And if I go to DC, I only have to draw 730 watts. So that's the difference measured on the power side. So just apples for apples. On the mains, on the 220 volt main, 230 volt mains, here we have same network, same cables. With quasi-square, we have 961 watts, and with DC, we have 730 watts. So that gives us a saving of 248 watts, and that's 26%. That is if we go to DC voltage. And then it's not only that we have this DC voltage helping us here to reduce the power, and because the current is lower, the voltage drop is lower, because the power loss that we have on the coax is lower, and therefore the voltage that you would measure everywhere around your network is higher. Especially when nowadays people start to add small cells or Wi-Fi hotspots or different components to a cable network. But all those components draw current out of your network. And the higher the current, the higher the power loss, therefore the voltage will be lower. If the voltage gets lower, the current even gets higher, and it will find a new balance somewhere. But it's very clear that the higher the current I have in the network, the lower the voltage will be, and my power consumption only goes up a lot. But by having DC, my voltage stays much higher because I don't have that high current anymore, and therefore the voltage I have everywhere is higher, therefore the current will be lower, and I can add more components to a network. Those components can now be fed out of a network, well, maybe with quasi-square or with sine wave, we couldn't do. Just because the current is lower, we can go deeper in the network and we have more power to give. Still, of course, to add components to it will raise this number, for sure, because they draw power from it, so it will raise the number. But in this case, it was not even possible, while here it is. And that's a big difference, that small cells or Wi-Fi hotspots in the network with DC powering can work instead of adding additional power sockets. We see operators nowadays adding more and more power points in the network to be able to feed additional components. And maybe if you go to DC, you don't have to do that because you have more power to give. It's not only that we have this part, it's also a side step. What do we have if we have power, if we have battery backup? Same networks. I have here, as we saw, we have 670 watts if you go to DC. We have 769 watts if we go to AC. And then here we have to put in 961 watts, and here we have to put in 713 watts. So if we just put a battery backup system, let's say 36 volt, 100 amps hour, and that's the battery that is mostly used as a backup system. So in this case, I go from a DC to DC converter to make it, again, the voltage I need, while here I need to put in a DC to AC converter. So the efficiency of a DC-AC converter is worse than the efficiency of a DC-DC converter. So here you talk about efficiency up to 96%, while here maybe you talk about efficiency of 90%. High numbers, but not equal. This one is better. And your current is lower. And therefore what you see is that the power I have to draw out of my battery, in this case, is 698 watts. And in this case, is 854 watts to do it this way. And that is 0.9 versus 0.96 efficiency. So the uptime of this battery here is about 4.1 hours, while here I have 3.3 hours. So I almost have same network, same cables, same battery, everything stays the same, but I have almost 1 hour more uptime of my battery compared to from AC to DC. And that's because, again, because the current is lower and I don't lose all the energy in my coax. This is an example what you can do with the batteries, and that's important because nowadays batteries have changed. In the past we all had the lead acid where we had the batteries like this. Nowadays we have a lot of lithium ferron phosphate batteries, and they have a much more constant energy than you have on the lead acid batteries. But what you also have is this part. This makes it very critical. Lead acid batteries are very sensitive of discharging. The further you discharge, the shorter the lifetime of the battery is. So you can see this, the cycle capacity is highly depending on the depth of the discharge. That's what you have with lead acid batteries. And your operators therefore typically say, okay, if it gets below this here, I just stop. I just cut the frequency here, the loading here. Well, you don't have that problem with lithium ferro phosphate. So this gives you an idea. If you go to the depth of the batteries, when you go to 100%, maybe you have 30 cycles or 300 cycles to repower it. While if you go to 30% discharge, it will be about 1,000. So the further you discharge it, the quicker the battery will die, will stop working. But you don't have that problem with lithium ferro phosphate. And now in this case, you can use thousands of time and even go all the way down to 100%. So I know this is a side step, but it's important that you can see, especially when you have lead acid batteries, discharging is very critical. And in my previous slide, I showed that because the current is lower, the efficiency of the DC-DC versus the DC-AC converter is better. Therefore, the uptime of the battery is longer. Therefore, you don't have to discharge your batteries that far. Therefore, your lifetime of your battery helps you. So it all comes towards you in a favorite way by reducing the current in the network. Sidestep in the batteries part. So far, the good news. Every good news also leads to bad news. So okay, we have pros and cons. So the pros of DC powering. The pros is, as we saw, we have a low power consumption. We have less stress in the network because we saw that we have these peaks. And normally when you have 50 Hertz, you have 100 peaks per second. Current peaks in your network. When you have DC, you have a constant flow. And therefore you have less stress in your network. And therefore at the end you have better MTBF. You have a power factor of 1. You don't have to worry about power factor of your amplifiers and stuff like that, because in DC you don't have that problem. You have a longer uptime of the battery, as you can see, 4 hours versus 3 hours, and therefore also the lifetime of the battery is much better. Those are all the pro sides. Now the con. If I look to the con, DC powering. DC powering causes corrosion. I will explain this later in a few slides, and that's an important part. One of the reasons why DC powering has never been used before is because corrosion in the network, nobody wants that. And the other part is, what do we do with surge in the network? So it's not surge to the transformer, but surge in the network. I want to explain both of those parts. Let's start with corrosion, the con one. Corrosion comes from the movement of ions. So you can see here, corrosion, I stole this from the internet, is the corrosion is related to the movement of ions. And with DC flow, because it always goes in one direction, you get corrosion. And with AC, because it constantly moves from left to right, right to left, it moves around, you don't get that corrosion. And you can see this when you have a sine wave like this, and you have your amplifiers like here, you can see that the current goes in one direction and the other direction, one direction and the other direction. And this stops the movement of ions. It's not transported further on. It just stays on the same place. It moves around a little bit, but that's it. You can see that therefore the current that you have, the net current in the network is 0, because you have a positive and a negative current. And therefore you don't move the ions, and therefore you don't get the corrosion effect. Everybody knows the difference between the network, what we have in the cable network, or for instance in telco where you have DC, they have a lot of struggles with that part. So this is something that will help you. If we have DC, we have a voltage going in one direction, and therefore we have a current going in one direction, and therefore we get corrosion. And that's true. So we want to solve this. And a way how we want to solve this is as follows. We go to a switched DC network, or a low frequency AC signal. So we have, for instance, 89 volt positive, and then we go to 85 volt negative. And then on a certain time we go back to 89 volt positive. So we constantly switch the voltage by creating this to avoid the corrosion. So still a DC signal here, a DC signal here, and a DC signal here, but we swap the DC to create a positive and a negative current, and therefore we also have this 0 current flow, and therefore we don't get the corrosion. This is the way how we solve this problem, and the way how we switch is important, because we don't want to, yes, okay, 89 volt, click, minus 89 volt, because then you get a lot of harmonics in your network, and nobody wants that. So the way how we want to switch in this part is in fact the same way how we switch also with an AC network. So when you have normally half a sine wave here, we also have half the sine wave here. So we have exactly the way how we switch from positive to negative, from negative to positive, the same as what we had before when we had the sine wave. And this will prevent all the harmonics, etc. in the network. So this solves two problems. And this solves the problem that we don't get the corrosion, and also now doesn't create the problem, let's solve that way, doesn't create the problem of harmonics. By switching positive, negative, we avoid this. So, but then it becomes important, how often do we have to switch? And what is it? Do we have to switch once a day, once an hour, once a second? And we did a study of that. And not only us, we also went to an official test lab called TNO in the Netherlands. And they did a big research for us. What is the sweet spot of switching? What is it where the corrosion starts? First thing we looked into the saving. What is the saving that we get? So let's say that we have 60 Hz for the US or 50 Hz in Europe, and say the saving on that moment is 0. It's the same. This is, I just compared DC versus AC. So if I would switch on 50 Hz, I have the same as when I would have a 50 Hz sine wave. So that's the same, so no saving at all. If I go to full DC, I have 100% of my saving. So in my previous example, I showed you the saving of 26%. So with DC, we have a full 26% saving. And the faster we switch, it becomes a linear line. That means that if we have a lower frequency, if we start switching, the profit that we get from DC to AC is reduced. So the saving that we get out of it is less and less the quicker we start to switch. Now we add in this graph, we also add the corrosion. So the corrosion, in fact, looks like this. It's not our research done by a professional house that understands metal work. We only understand RF. So I said, okay, what is it that what we need to do? And this is how the curve goes. The corrosion is almost 0 until you get very close to this. And that means that roughly between 1 Hz and slower starts to create corrosion. Based on that, we came to the conclusion that probably in this area here is the sweet spot, because we still have 95% of our saving while we have no impact of the corrosion. So around 2.5 to 3 Hz is where the sweet spot is. So we say that, let's say 3 Hz or 2.5 Hz in the Netherlands will generate about 95% of the saving and has a very limited impact on corrosion. This frequency here is the frequency that we want to use now for our switched DC or low frequency AC. Yeah, how you want to call it. Oh, sorry, I moved my microphone. So this is the frequency spot that we want to use for our switching. So that was column number 1. Then we have column number 2. What do we do with surge? We got this question from an operator, and we thought it was a very good question. And I tried to put it in even what the problem is, the presentation. So let's say we get surge on the coax, not direct hit, but we pick up the surge. That voltage will travel over the coax and go into your amplifier. And that will damage your upstream and downstream amplifiers. It's very simple, it's a high voltage, it stops doing it. And it doesn't matter if it comes from the input or the same way, if it comes from the output, it comes into your amplifier and it will simply destroy your amplifier. This is a problem that we have, and to avoid this problem, we start to add protectors for this. And we call that gas tubes, seductors, surge arresters, same idea. It's components that we connect to the input and to the output, to every connector that we have in the amplifier, and that has to protect the amplifier. And the way how that works, if we have a surge like this, and that surge will come into the amplifier, the protector will close, and therefore the surge will go to ground and disappear, and will not damage your amplifier. Every amplifier is built this way. Now we get a problem because this is now closed. And the only way this will release if I have a 0 crossing in my voltage. So when we get a 0 crossing, this will release again. But with DC or switch DC or low frequency AC, it can take a long time before we have that zero crossing. And therefore, we have a long time that this amplifier is out of use because the input is just short circuit. That is something that we have to address. We cannot wait till the next zero crossing comes. Because if you are unlucky, it can take over 100 milliseconds, and nobody wants that. So the way how we want to do this is, I try to picture this in this page here. So here we have our AC-DC converter. And from the AC-DC converter, we go to, we call that a polarity switch, an H-bridge. So it is something that creates a positive and a negative signal on the coax. The voltage on the coax. So when it is positive, and this one will conduct to this one, whether this is the negative side and this is the positive side. And when you turn it around, then this one will conduct, this one will conduct, and then it turns around. Then we have a positive or a negative voltage. This is something that's H-bridge, and that H-bridge then delivers the power and it comes to this amplifier, as we just saw. And now we get a voltage. We get a surge here. And that surge then will create that one to close. Because it has to protect the amplifier. But as you can see on time, I still had to wait a long time before I'm going to get my zero crossing here. So the way how we solve this is that we're going to measure in a microcontroller the current. We constantly do this. And at the moment this closes, it will detect that the current is changing. And if the current is changing, then we generate a number of zero crossings just to release that switch. That's needed so that we don't wait. The moment it happens, we directly generate some zero crossings. If the change of current was happened not by surge, but by something else, nothing happens because we just have our normal signal. We just have a few zero crossings. So there is no downside of that to generate it. But if it was caused by surge, this is the place where it will release. So here we release then that switch again. That's the idea how we want to address that part. So how we're going to build this? This is a way how we build our, we call it ASP89. So it is the access smart powering 89 volt. This is a unit that we have tested by a number of operators, also in the US, where we generate this 89 volt. And in Europe, we tested it with 72 volt, so different voltages, just to compare how that goes. So we had a DC of 72 volt in that case. Just a normal output that will go onto your coax. So what we have is we have our input, normal power input. Then we can have two times a power supply inside, a switch mode power supply, and we have the battery backup system. The backup system means that we have a battery charger on this side, and then we have the DC-DC converter on this side. Anyhow, this H-bridge has now three 89 or 63 or whatever voltage we choose inputs, and will generate the switching going on to the coax. There is a microcontroller to control all of this. Also detect if the current is changing, and if the current is changing, generate a couple of the zero crossings to release surge arresters if it was caused by the surge arresters or the seductors. That unit, of course, will have their own memory and stuff like that. And we have, for instance, a Doxer transponder or a different way how we want to do it. And we have a USB connector, we have different way of communicating to the device. It's not complex, it's very simple. We have these parts, and then we can have different blocks. We have them from 550 watts, we have them from 900 watts. So in fact, one is 550 or 900. If you have two of 550, you have 1100 watts, you have 1400 watts or 1800 watts. It's by just choosing what power supply we put into the system. All of this is always the same. It's always the same problem, same product. We just put in the power supply that you want to put in. This is the way how we want to build this. And this is the way how we tested this. And as I said, we have different results. We have some areas where we have over 30% saving. Live network, tested, compared apples for apples. And we also have them where it was about 20% saving, but that was just because it was short cables or whatsoever, didn't have a lot of loss there. The average is that it is somewhere the saving is somewhere between 25 and 30%. But of course, it all depends on a lot of factors. Depends on how your network is built, depends on the voltage that you have at the moment, depends on the coax that you have now, how many amplifiers you have, how much power you have out of the amplifier. Do you have sine wave power supplies or feather resonant transformers, constant voltage transformers? There are a lot of different facts relate to this, but the bottom line is that low frequency AC or switch DC give you a lot of benefits because you just reduce the power and you can build this with a much higher efficiency than with a normal transformer. And the combination of those two will bring you a lot of extra options for your network. Can reduce your OPEX, be more green, but also can give you more power to give away into the network. So we thought this was a nice line to put in here. Is just because it has never done this way, doesn't mean it cannot be better than the way how we always done this. So we thought this was the way how we first do. And if you type this in on the internet, you're going to get this nice picture that somebody tried to drag around a car with square wheels, and somebody offering a better solution, and they say, no, sorry, we are too busy to change this. So the goal is that we believe this is a good way going forward. You don't have to change your network. You can keep everything as is. Just change the shape of the power that you put on the network. And that way you will reduce the power consumption in your network. That was my goals of the presentation. So I will hopefully cover them all. I said in the beginning that during my presentation, I want to explain how to save power, lower power consumption, be more green, get closer to your net zero goals, and lower the OPEX. And we do this by just changing one product inside the network. I don't know, Lisa, you received any questions?
Yes, we've had a couple of questions here. Besim Latifi asked, can this application have application in HFC only or also in different industries?
It's a good question. We looked only so far into the HFC industry. But it's clear that the telcos normally work on minus 48 volt DC. So they already have that step, but they have the problem with corrosion. So yeah, maybe. We have not looked into this, but at the end, if you look to it, I saw some research on even on houses. Everybody now gets 220 volt AC into their house or 230 volt. If that would have been a DC signal, also in the house your power consumption will drop. And that's the same part because you have a lot of all your equipment in the house is DC. Your LED lighting, your oven, everything works on the DC signal. So we have a lot of converters from DC to AC. By just starting with DC, at the end, your power consumption will drop. Because even in the houses will work. And nobody knows what happens in the future, but this becomes definitely a higher topic. You can see already this is used also in the high voltage lines. If you look to the high voltage line between Norway and England, they already used switch DC. It's not. It is something to be able to have a higher power through your network, reducing the current, because at the end, the current in your network causes losses. Reducing the current will help you to increase or decrease the power loss and therefore have more power at the end.
Okay, thanks very much. That's great. And we have another one. This is anonymous. I'm not quite sure who's posted this, but the question is, even 10% saving in 1 million cost of power is 100,000. In 12 months, you get 1.5 months free electricity. I hope this makes sense. 30% is 300K, meaning more than 3 months free electricity. That makes sense to you? The numbers there.
The numbers. Yeah, there is definitely a return on investment on this part. And I don't know the numbers that you just mentioned, but it is true I see big operators, they have power bills of tens of millions of euros. Yes, 25% is a lot of money. But of course, you have to replace the transformer. That's also an investment. So we had different calculations, and we love to work with operators. We have some of them where the return on investment was less than 6 months. And we have some of them where the return on investment was 4 years.
Right.
It's somewhere between those.
Okay.
The reason why it was 6 months is very clear. They started to add a lot of extra components in the network. Because of that, they have to start installing a lot of extra power points there, transformers, to feed all those additional components. And they didn't have to do that with this way of feeding the network. And now they didn't have to add all those extra power points, and adding a power point is very expensive.
Okay.
But the return on investment was less than 6 months. But I would say, let's say that if you just have apples for apples, ferro resonance versus that low frequency AC, the return on investment will somewhere be around 3 years, 4 years, somewhere in that area.
Right. Okay. Okay. Thank you. Another one, Sam Kohler has asked, have you done a total cost of ownership for the solution with ASP89 for any customers yet?
No, it's a good question from Sam. Always have good questions. So no, we don't. We only look to the return on investment in this part. We still want to work with operators more and more about this. What would they do? Because now we are just focusing to the power bill. But we don't look at how much would this increase the lifetime of amplifiers? How much would this help in different areas as well? Because we are lowering the stress in the network, MTBF will be better. So there are a number of extra parts in there that are at the moment just difficult to quantify really what the total cost of ownership will be of this solution versus the traditional way. So at the moment we're only focusing on power reduction. That's the only part, and that already gives you a good return on investment. All the other parts will just help on top of it.
Okay, that's clear. Thank you. And I'll have one from Jürgen Brenner. Why 72V were chosen for Europe? And he said in brackets, actually 66, 65V are used.
Yeah, true. There is a low voltage directive. That's how it is called. And the low voltage directive says that the maximum top voltage that you can have on an AC signal is 65 volts.
Right.
That's what they use. It also says that the DC voltage that we can put on the network is around 85 volts or 80 volts. I don't know really the number. So the DC voltage that you can put on the network is higher than the AC voltage that you can put on the network. And it all relates to how dangerous it is for humans. To be the low voltage directive is a safety standard. And the DC voltage can be higher than the 50 hertz AC voltage. So we started with 72. Also because it was very simple, there's a multiple of 24, so we could have a multiple of 24 volt power supplies where we started this project. But we're open for whatever the customer wants it to be. There's changes in the safety standards happening at the moment. The NEN is discussed again, the low voltage directive is looked at, can we do things different? So in our calculation here, we thought, okay, let's just keep it simple. We just go for apples. It's a 89 volt top ferro resonance versus a 98 DC. I think in Europe it's different because the DC voltage can be higher than the top voltage. So it even helps more.
Right. Okay. Thank you. Gerald Nickel has a question. Any long-term experiences on the effects of switch DC on the amplifier's power supplies? Can they handle these low frequencies?
Yeah, they can. Good question. Every amplifier nowadays, every modern amplifier, let's call it that way, nowadays have a switch mode power supply. Switch mode power supplies works all the way up from DC all the way up to probably 100 hertz or something like that. So it can be all different frequencies in there because at the end we're going to have the rectifier on the input and we're going to have the capacitor after that. So going to DC will work perfectly. In fact, in the lab we even use DC to power the amplifiers for test. So DC works perfect and also AC. And the frequency, as long as it's not too high, will be no problem at all.
Okay.
So So yeah, it's a good question. We got a question before, said, oh, do we have to change something on the amplifiers? And the answer is no. Every modern amplifier will do this job.
That's good to know. Okay. Diego Royo said, Gerald Nichols, a good question that will explain why just one product changed the network. Sorry, Diego's just making a comment that it's not a question, sorry. I have someone anonymous here saying, what kind of safety mechanisms did you implement with that product? There's quite a few here, so that's the first of many.
Yeah. It's probably also the part that we need to address very carefully. Safety, of course, we have the switch mode power supplies are safe, which used everywhere in the world, all over the place. But it's very clear if you have a ferro-resonant transformer, is this block of iron. If you hit this with 6 kV voltage, it would not even blink. There's a lot of energy that you can put in that unit before something goes wrong. Switch mode power supplies are sophisticated, fast switching devices. And the protection that we have to build around here has to be absolutely perfect. Because the last we want is that you hit it with a 1, 2, or a 6 kV voltage and it will have an impact. So we put a lot of safety equipment around the device that on every connector you can hit with 6 kV to meet all the safety requirements that we have in all the specifications of the products to have a switch mode power supply the same way as what we have with the ferro-resonant transformer.
Okay, thank you. The same person wants to know, what about DC stray currents in cable ducts owned by another operator?
Sorry?
So what about DC stray currents in cable ducts owned by another operator? Does that make sense?
I'm not sure if I understand the question.
Maybe it's well, and then it says, what about interferences with DC systems or stray currents being collected from private buildings, such as photovoltaic installations and roofs?
Now, I'm not sure if I understand the question, but what I can tell about DC current, you have DC. And we got also questions, so what if we power from 2 sides, for instance, and do we then have to sync one switching with the other switching and parts like that? Not sure if that was the question. In our case, that's not. At the end, if we feed the network from both sides, we always use a galvanic isolator that is needed, otherwise one transformer will hit the other transformer. And that galvanic isolator will stop this part, so therefore you don't have that issue where you have voltages from 2 sides.
Okay.
We did a study on it. Do we need to synchronize the parts? Do we need to build an extra PLL in there to be sure that one voltage will follow the other voltage? But that's not the case. So in our case, we'll have the galvanic isolator in the middle, and then you can have AC on one side and DC on the other side, because that will not harm each other.
Okay, great, thank you. David Zilberberg wants to know, is it possible to use 90 VDC batteries for backup without the need for converting DC-DC 36 volt to 89 volt?
Yeah, sure. I just use it as an example. 36 volt battery is just used as an example to do this, because I know this is mostly used. At the end, we're going to build a DC-DC converter in there. And as long as the output of that DC-DC converter is at 89 volt or the 72 or the 65, whatever we want to have for that customer, it's always the same.
Okay, great, thank you. I think we're kind of running out of time, so it's probably one of our last questions. There's 2 more to go. In South Africa, we have regular power outages from the utility provider. This is from Angelo Carrera. Exchanges need to have battery backup, and at times the outages are longer than scheduled and the batteries go flat, which brings down the exchange. Could there be an application for the ASP for this challenge?
Yeah, perfect question. Yes, that's one of the things when you look to it, just comparing apples for apples, the uptime via the ASP versus the additional way is almost 25% difference. So if your old system can do 4 hours, the new system can do more than 5 hours. So it still is, on a certain moment, every battery will go flat if you have it to a long time. But it's very clear, it is that the power that you can get out of this system at the end because the current is lower, your battery going to have an easier life. And therefore, this is a perfect example. While we started this, because we had also customers, for instance, from Canada, they said, "Oh, we are struggling of hitting 4 hours power backup because they have big networks." And so we tested this, and with this way, same battery, we could hit the 4 hours, while the old system could just do 3 hours.
Okay, great. Thank you very much. That's great. And finally, May Lai has said, I may have missed part of the presentation, so I have a question. Most of amplifiers in the markets are AC powered. If ASP is deployed, do existing amplifiers have to be changed?
Yeah. So no, I think we answered that. No, that's not. No, you don't have to replace that. As I said, we all have switch mode power supplies inside the amplifiers, and therefore that will not affect. Every amplifier nowadays can have DC or AC or 3 Hertz or 10 Hertz or 50 Hertz loading, because at the end you're going to have your diode bridge on the input, creating a DC signal via the capacitor.
Mm-hmm.
If you hit this with DC or 3 Hertz or with 50 Hertz, will give you the same results.
Okay, thank you. We are running a bit short of time. One more quick question from Jürgen Brenner again. What battery voltages could be used for ASP72, 36 or 48 volts?
Both.
Sure.
It doesn't matter. You have a DC-DC converter, and you can use both of those batteries. If it is 12, 24, 36, or 48, it doesn't matter. At the end, it is the total power that you can get out of it. If you have 36 volt, 100 amps per hour, then you can have 3.6 kilowatt per hour out of there, and that will do maybe in our network over 4 hours. If you have a 48 volt, 75 amps hour, I roughly end up with the same number, and also we can do 4 hours. So that's the same. Just the power, it's the kilowatt hours at the end that you can get out of it, will bring you the uptime. But the voltage, the big advantage of this is that the voltage is not important anymore, because we have that DC-DC converter. So if you hit it with 36 volt or with 24 or with 48, the output is always 89 in our example, and will always do the job.
Okay, that's great. Thank you. It's really clear. I think that kind of wraps it up. We're sort of running out of time, but I thank you so much, Jan. You've done an amazing job there. It's really clear, and thanks for all the questions that you answered, and thanks for our audience as well for asking loads of questions. Really appreciate it. This will be featured on our YouTube channel in a couple of days' time, so look out for it if you miss anything. You want to go back to it. And Jan, is there anything you wanted to add?
No, I missed one question. I thought somebody will ask that, so I thought I will save that. So I will maybe then ask the question myself. Is DC more dangerous than AC? Because that is something that we often have as a question. Say, yeah, but we have the safety requirements, so DC is more dangerous than AC. And that's the other way around. In fact, at the moment we use 50, 60 Hertz. And if you look to the human body, that probably is the worst frequency we can choose, because that frequency will react on our muscles, react on our brains, and will just stop the whole system.
Okay.
For example, 50 milliamps will kill you if it is 50 Hertz. But if it was 3 Hertz, you can go all the way up to 150 milliamps before it kills you. So the current that you can put into your body on a lower frequency is much higher before it really starts to. It will always hurt, I think, but will stop the system. So we did get a lot of questions in this in the past. He said, yeah, but when we go to DC, we need to have extra safety requirements and things like that. And the other way around. I didn't choose 50 Hertz in the past, but I think if we will do it all over again, I don't think we'll use again 50 Hertz, because 50 Hertz is very dangerous for the human body compared to 1 kilohertz or 3 Hertz. As an example.
Yeah.
So that's now. I think I'm glad that you. It's good questions. I really like that part. As I think you said, Melissa, we will post this. If you have any other questions, just reach out to us, please. Really just to show that there are different ways of doing it. And one of the texts was that just because we have never done it this way doesn't mean it cannot be better. And I think this is a good example of it, that by just changing the shape, we can save, at the end, we're going to save money. And that way we can be saving OPEX, and that way we can be more competitive to our competition.
Absolutely. It's never been more important, has it?
Yep, that's the goal. We all need to be in the business. So helping our customers helps us.
Absolutely. Thank you. No, you're quite right. Well, thanks again, everybody. Really appreciate it. Have a very Merry Christmas, and we'll see you in the new year.
Merry Christmas.
Okay, thanks very much, everyone. Take care. Bye.
Bye.